On February 7, 2008, an ordinary night inside a Georgia sugar refinery became a disaster when a single hidden spark turned tons of everyday dust into a rolling wave of explosions. 14 lives were lost, and 38 were injured, all because sugar dust behaved like fuel in plain sight. How does something as innocent as spilled sugar become the driver of catastrophe? The answer lies in what was building above the factory floor, unseen until it was too late. Inside the Imperial Sugar refinery, dust wasn't just a byproduct. It was a constant companion to every shift. Granulated sugar moved through an intricate web of bucket elevators, screw conveyors, and belt systems, each designed to keep production flowing. Every transfer point, every spill, and every misaligned belt released a fine cloud of sugar particles into the air. These machines leaked and scattered sugar dust as they carried tons of product from silos to packaging lines, leaving a trail of powder in their wake. Even routine operations like pouring, milling, or bagging sent invisible clouds drifting onto beams, ducts, and rafters high above the floor. Over time, these layers thickened, settling into corners and onto surfaces rarely cleaned. In a plant built for volume, the machinery that powered efficiency also created a steady, invisible fuel load, one that built up day after day, waiting for the right conditions to ignite. Sugar dust, when suspended in air, can behave much like a fuel vapor. The danger comes down to concentration and confinement. When sugar particles are finally milled and dry, as little as 30 grams per cubic meter in the air is enough to reach the minimum explosible concentration. In this state, a single spark or a hot surface can ignite the dust, creating a flash fire or an explosion. Scientists measure the violence of these dust explosions with a value called KEST. For sugar dust, KEST typically falls from 125 to 155 bar meters per second, classifying it as a strong deflagration risk. In a confined space, such as a tunnel or an enclosed conveyor, pressure from the initial blast cannot escape. Instead, it builds rapidly, turning what would be a small flash into a powerful pressure wave. This is why sugar dust, invisible and ordinary on the floor or on beams, can become explosive when it is airborne and trapped. The architecture of the Imperial Sugar plant shaped how danger accumulated long before anyone noticed. Decades of expansions created a maze of interconnected corridors, narrow tunnels, and equipment-packed rooms where air barely moved. Overhead conveyors ran through steel-clad chutes and enclosed passageways, some stretching more than 100 feet beneath the silos. These confined spaces, meant to protect product from outside contamination, trapped dust instead. Without proper ventilation or dust extraction, sugar powder collected in the shadows, on cable trays, above drop ceilings, and inside the hollow spaces behind panels. Even minor leaks or spills could go unnoticed for days, feeding layers of fine dust into places where cleaning crews rarely reached. The plant's dense layout allowed dust to build up quietly, turning every corner, duct, and crawl space into a potential reservoir of fuel. In this environment, a single spark would not just ignite a fire, it could set off a chain reaction through the very bones of the building. Beneath the main silos, a steel tunnel stretched 130 feet, running the length of the refinery's foundation. Inside, a belt conveyor carried granulated sugar from storage to the packaging lines. In 2007, the conveyor had been fully enclosed with steel panels, a change meant to keep out debris and protect product quality. But the new enclosure also sealed off airflow, turning the tunnel into a confined box where sugar dust collected out of sight. Dust from spills and routine leaks settled onto every surface, building up in drifts along the belt and in the corners. With no integrated dust extraction or venting, the air inside grew thick with fine particles whenever the conveyor ran. On February 7th, just after 7:15 p.m., a bearing deep in the tunnel began to overheat. Friction from the moving parts, unchecked by sensors or regular monitoring, created a hotspot. In the oxygen-rich, dust-laden air of the sealed tunnel, a single spark or hot surface was all it took. The enclosure that was supposed to keep the sugar safe had instead created the perfect conditions for an explosion. The first explosion tore through the steel tunnel beneath the silos, sending a shockwave down the length of the conveyor. In that confined space, the pressure had nowhere to go. The blast ruptured the enclosure, blowing open panels and forcing a cloud of sugar dust into the air above. Within seconds, the pressure wave raced through connecting corridors and utility chases, lofting dust that had settled for months on beams, pipes, and rafters. Each new pocket of airborne sugar became potential fuel. When the initial blast hit these clouds, the ignition leapt from room to room, multiplying in force. Secondary explosions thundered across the packaging building, shattering windows and buckling floors. The violence of these blasts was driven not just by the first ignition, but by the chain reaction, each pressure wave dislodging more dust, each fresh cloud feeding the next explosion. In a matter of moments, what began as a single rupture became a facility-wide cascade, turning accumulated dust into a series of fireballs that swept through the plant's core. Inside the Imperial Sugar plant, the explosions left workers facing a nightmare of smoke, fire, and blocked escape routes. In the first moments, corridors that had served as daily passageways became impassable, choked with debris and flames. Stairwells collapsed, doors jammed shut from warped frames. Some workers were trapped deep in tunnels beneath the silos, cut off from exits by falling rubble and the relentless spread of fire. Others tried to reach safety, but found the air thick with smoke, making every breath a struggle. Emergency crews arrived quickly, but the building's instability forced them to move cautiously. Portions of the packaging building had already buckled, and new explosions threatened to erupt at any moment. Amid the chaos, survivors helped each other to the few clear exits, carrying injured co-workers through darkness and confusion. 14 people lost their lives, many unable to escape the maze of collapsed corridors. 38 more suffered burns and injuries, some severe enough to require weeks of treatment. The rescue effort stretched into the night, with firefighters searching for missing workers in a structure that could give way at any time. The scale of loss was immediate and devastating. Families were shattered, a community left in shock, and a plant forever changed. Years before the disaster, official documents warned of the risks hiding in plain sight. Insurance inspectors in May 2007 flagged combustible dust as a hazard at the Port Wentworth plant. Yet the paperwork shows only minor recommendations and no urgent calls for dust extraction or explosion venting. OSHA inspection records dating back several years noted housekeeping lapses, but did not cite the facility for dust violations. By late 2007, the main conveyor beneath the silos was fully enclosed, yet no dust collection system was installed. Internal safety checklists and routine audits failed to address the growing fuel load. The Chemical Safety Board's 2009 report later traced these missed warnings in a timeline of overlooked hazards, each one documented but never fully confronted. Investigators from the Chemical Safety Board found that the failures at Imperial Sugar ran deeper than any single piece of equipment. Housekeeping standards were not enforced, allowing sugar dust to accumulate on overhead beams, ledges, and machinery. Dust collectors were missing or undersized at key points like bucket elevators and transfer stations, leaving clouds of fine particles to settle wherever air currents carried them. When the main conveyor was enclosed in 2007, no hazard review was conducted to assess how the change would affect dust accumulation or explosion risk. Safety audits and routine inspections failed to address these gaps, normalizing hazardous conditions over time. As one chemical safety board investigator later noted, the system was set up to let fuel build quietly, unchecked, until disaster struck. Preventing another disaster starts with clear standards and constant vigilance. The National Fire Protection Association requires every facility handling combustible dust to conduct a dust hazard analysis, documenting every point where dust can accumulate and ignite. Operations leaders stress the need for temperature and vibration sensors on bearings, especially inside enclosed conveyors. These sensors detect early warning signs of overheating before friction can trigger an explosion. Routine cleaning of overhead beams, ducts, and ledges must be enforced, not just scheduled. Dust collectors should be connected directly to transfer points, and enclosures must include both ventilation and explosion venting. As one plant safety manager puts it, you cannot control what you do not measure. Monitor, clean, and vent every space where dust can settle or escape. Today, more than 150 industrial dust explosions still occur each year in the United States, despite decades of warnings. Industrial dust is not just a housekeeping issue, it is a hidden fuel. As long as dust is overlooked, the risk remains. In every factory, prevention is a daily life or death decision.